symplectic sigma model, I got slightly conflicting instructions about how to prepare the talk and who it is for. So I decided to reach back to an old experience from when I was in charge of my undergraduates in college in Cambridge. And I told the graduate student who was organizing the examples class to make sure he covers all the basics. That's the important thing. But then there will be some people who will be bored. For example, in this case, those who have heard me talk about these things before. So I said, well, what you can do is bring some tricky questions and write them down on the board at the beginning of lectures, and then some people will think about those and they tune in when whatever you're explaining is something they need to hear. So he took my advice and came into the lecture room and said, Dr. Teleman told me to bring some tricky questions for the bright ones among you. So, all right. In this spirit, all right, let me say something. What I'd like to get, and it's the only new thing that I'm suggesting for people who've seen this story before, and then the rest of the talk will be trying to explain that. So I'm going to use this throughout. So X omega is a compact symplectic manifold. You could do without compact, but then you have to change something. And G acts on X. It's a Hamiltonian action. And moment map is mu. And I'm going to look at the GIT quotient. I assume it's good in the sense that it's an orbifold at worst, so I don't quite know a standard notation for this. Let me do this. It's mu inverse of 0 divided as the G as an orbifold. And there is something mapping to it, namely an open dense part of X, the open cell for the Morse flow of mu squared. Whoops. Morse flow. And the fiber is the cotangent bundle of G, actually. The theorem, I know, the classic theorem of Guillemin Sternberg tells you that you have a disk bundle, that the cotangent bundle that's actually symplectomorphic, very strictly to a tubular neighborhood of the inverse image of the moment map. And so I'm going to write some things down which are partly science fiction, but in some cases actually they've even been proved. So we're going to look at, so maybe to put some names here, so Wancha, Ritter, and there are conditions for the theorems I'm describing. So let's look at the first statement I'm going to make is that the symplectic cohomology of X naught is the quantum cohomology of this orbifold quotient with coefficients in the symplectic cohomology of the fiber, which is also the homology, the shifted degree of the base loop space of G. And because of the G action on the fiber, we have a topological, let's say, LG action here. In other words, we can take the LG equivariant version of that, so make it LG equivariant. That means add in at the base the cohomology of the classifying space of LG, but the classifying space of loops in G, and maybe I'll make life easy, G connected, just to make life easy here. It's not really a restriction. BLG is also equivalent to the group manifold G divided by its own conjugation action. So, in other words, we can talk about the LG equivariant symplectic cohomology of L naught, of X naught, and that is the cohomology over G with coefficients. Sorry, the cohomology over a space G equivariant for G with coefficients, the symplectic cohomology of x naught. And according to this, what it does exactly, it kills the coefficients, because the action is on the coefficients. You're taking equivariant cohomology for translation actions, you're losing the coefficients. So that's meant to be just the quantum cohomology of the quotient. At the same time, x is the compactification of x naught, so general philosophy tells you that should just be quantum cohomology of LG equivariant quantum cohomology of x. And by what I said above, this is meant to be the cohomology, equivariant cohomology of G, of the group manifold G with coefficients and local systems whose fiber is a quantum cohomology of x. So here I should say deformation. Maybe I'll put this up. So you're led from here to conjecture this equality, which describes the quantum cohomology of a GIT orbifold in terms of some structure on the quantum cohomology on X. And of course, I mean, there's a lot of science fiction without any assumptions, but in fact, the spectral sequence, the Leray type spectral sequence I wrote up, is known to hold some fairly restrictive assumptions. So it's not complete science.
When you write the equality on the right, you mean deformation?
Deformation, yes, you're correct. But part of the conjecture I'm going to state in the Fano case, there's no zeroth order deformation. The conjecture is pretty thinly supported, though. So maybe let me state that now. So, and I should underline that because you'll see it's not a trivial coefficient system. So let me state a theorem and then the conjectures will go with that. So theorem means I think I can prove it. Doesn't mean I've written up the proof. And there's some things which I'm not working on some parts of it because for one thing, I've given away some of those projects to my graduate students some time ago, so it's a bit uncool to keep going. So theorem is there is a local system, a G equivariant local system over the group manifold G, so over G, with fiber at the point, the group element G, equal to the Floer homology of the symplectomorphism induced by G on X, which is non-canonically isomorphic to the quantum cohomology of X in connected case. In connected compact case. Connected G compact X case. And the cohomology, so maybe that's a local system I want to call QH star underlined. H star G of the group manifold with coefficients in QH star is a Frobenius algebra if you use a group convolution. And it is a space of states in the gauged Gromov-Witten theory of X. And there's a conjecture that goes with that, which is more or less what was on the other side. The conjecture. So after deformation, I'm not saying anything about. Deformed, so maybe for deformation, is actually the quantum cohomology of the GIT system. And in the Fano case, no deformation is visible to first order. In the non-Fano case, actually, I don't even like the statement, it's very misleading. The truth is that this guy on the right is the summand here, so QH star really the summand. In other words, the algebraic calculation of this will give you a cohomology that's too big, as spurious states in the gauged model. And I like to, what's the conjecture based on here? Really, it is from the linear sigma model, from the computations in linear sigma model. And as a remark, if you take X is Cn, which is of course not compact, but let's take it anyway, and G is a torus, which is a subtorus of a diagonal in U1 to the n, and the quotient is Fano, I claim that the conjecture is actually the Batty representation of the quantum cohomology of the quotient. So you get the Batty representation. Of quantum cohomology of X divided by T as being the cohomology of Bt modulo the Zeidel relations. All right. So that's kind of the upshot of the talk, and the only new line I'm pushing. My knowledge of symplectic geometry and symplectic cohomology is not nearly good enough to opine as to how far this is from an actual argument in terms of technique, but for me it's a moral reason why you expect that, and this also will tell you what deformation we're talking about. It's a deformation generated by throwing away unstable strata from X, and in Tori case you can actually work it out, and if you do work it out, in fact I'm willing to bet you'll get one of the proofs of the Batty representation in that case. In that case you'll end up spelling out the proof in sort of different language. So I'm writing this because I wanted to point out I'm motivated by an answer to a question, which is, let's say you know X and you've computed say quantum cohomology of X. Can you actually compute something about GIT quotients? The answer, of course, is yes, because there are so many examples where the first GIT quotients computed by physicists were computed in this way. I don't think they studied it in this language, but in the torus case, of course, you can say it in a simpler language. So now I'll start with my actual talk. Any questions before I abandon this and return to it at the end?
So
yeah.
For the bright ones, we saw this during the lecture.
Sorry?
For the bright ones.
Yes, well, that's right. Try to prove the whole thing. No, actually, I think this conversion maybe takes a little bit of thought, probably, but not quite so much. The conversion from this formulation to the. So here's what's happening. Here I have a local system over the torus with phi by the cohomology of Bt. So the total cohomology in a generic enough situation will be the fiber modular monodrome is -1. So you just have to unravel that and see how these are the Zeidel relations. Maybe that's an exercise that can be done in reasonably short time. Probably a theorem it's hard to prove in a reasonably short time because I haven't defined actually the gauged Gromov-Witten theory. So let me say a few words about this now. So a few words, a few generalities on the gauge symplectic sigma model, let's say. And so Gromov-Witten theory, of course, the TQFT having to do with modular of stable maps, integration of a modular of stable maps, so integration of a over stable pseudo-holomorphic maps to X. So now if G acts on X, a physicist will immediately want to do one thing, or rather one thing in two steps, namely one, add a background field it would be a gauge field, but doing the gauge field in the form of a principal G bundle, P over sigma, so stable pseudo-holomorphic maps from surfaces, P from sigma, principal G bundle, and instead of maps from sigma to X, take sections. And they're pseudo-holomorphic sections of this. So to make sense of that, you need a complex structure on the G bundle. So I think in physics they would call that a gauge theory in a classical gauge background, where you fix a principal bundle. And you want to quantize the gauge theory means integrating over all bundles. So quantizing means integrating over bundles. And I'm keeping it so elementary because I want to explain the steps later in a slightly more abstract way. So I have to remember there are two steps here. And here is where you have to start saying a bit more. You have to start defining space, so you have compact space of integration. And here you have to start making choices. So you need a notion of stability of bundles and sections. So you get a compact moduli space. And there's more than one way to do that. So more than one way in cohomology to define moduli spaces. So there's fairly old work by Salomon and his student Ziltener, then Chris Woodward and Gonzalez. There is notion of stable maps, and don't want to go over all of it. I do have a favorite notion, which I believe gives a consistent theory. It's not written down. It's my favorite notion. Use these all holomorphic bundles. So no stability on the bundle. Stable sections, you can define that. And use K-theory to integrate. And it's pretty clear based on evidence that actually works, but it still has not been, the program still has not been completed. So two examples were done by myself and Chris Woodward. This was, today we'd say that what we computed was a mirror of a vector space of a representation of G. Of G. So in other words, the case on X of the representation. We didn't say it that way in those days because I didn't know what that meant. And another example to show finiteness. So finiteness was shown for X is a point, and G is GL1. Was done in a paper by Frenkel, myself, and Toland. And then the subsequent work by Pablo Solis, who defined the moduli stacks for nodal curves in such a way that I could have a hope of integrating over them. Defined moduli for nodal curves. And I think there's ongoing work with Gonzalez and also Tom Graeber. So there's a lot of people working to make sure that there is a well-defined theory, so it makes sense to integrate over bundles, even at least one version of gauge theory, and that's what I'm going to call the gauge theory. The reason why there's a choice, simply put, is that on the space of bundles and maps, you have two independent notions of stability because you have two line bundles. So you have a curve, a principal bundle, and a section. If you just remember the bundle, then you're mapping to G bundles on a curve, and there's a polarization on those, which you could use as an ample line bundle on the space to try to define a moduli space. There's another polarization you can pull back to X, not to G. You can pull back from the polarization on X, and you can then weigh them differently and get a whole family of moduli space, and this gives you one extreme of that. As the GIT quotient, if you like, the GIT quotient is the other extreme of the polarization, where the section lives only in the semi-stable part of X. In XO, where what I described was the first extreme, let's say first extreme, any bundle. First extreme would be stable bundles, stable bundle and any section. And the K-theory somehow contains them both, but if you want to get from K-theory to either of them, there's a choice to be made. So choice, let's say, of asymptotics will give you what's called one adiabatic limit or the other. So there is, in principle, a story that should give you meaningful answers. Since I've talked about cohomology, not K-theory, although you could put K instead of H, what I expect you would get is the one where you get the stable bundle in any section from the gauge theory as written. Whereas this one is the other extreme, hence you expect to have to do something to pass between them in general, because they're not the same. Those are two extremes of the homological gauge theory. Okay. All right, so now having talked about it, you'd like to compute it, and the question is, what information about X and G do you need? And the answer turned out to be more than was worked out. And in fact, it's always obvious in hindsight, and probably most people know it already, but so the question too, so where am I in my organization? Right, so let's say a twisted sector problem. So let's say you have X, G as before, and let's say you know what you want to know about the Gromov-Witten theory of X. What else do you need to supply to compute the gauge theory? To get gauge theory? And half the answer, turned out to be only half the answers provided by Giventhal some time ago in the algebraic case, where he looked at equivariant Gromov-Witten theory. So this is what gauge Gromov-Witten theory would be if the bundle was trivial. So the bundle is always trivial. Or equivalently, just consider the G action on the moduli space of stable maps. And one arrives at a definition of the equivariant quantum cohomology of X. It's going to be a Frobenius algebra over the cohomology of BG, that's somehow the ground ring. And from here you might want to compute the gauge Gromov-Witten theory, you see. And you find out it's not possible. So you don't have enough information. It turns out not enough information. To compute gauge, to gauge. You can suspect that because, as I said before, it looks at the case when the bundle on the surface is always trivial, so how can you tell what happens when you start moving the bundle? So it's not obvious, and in fact the information is missing. Not a huge amount, but some information is missing. So to see what's missing, it's helpful to think of the case of so example, G is finite. So in this case, if you use rational coefficients, equivariant cohomology doesn't do very much for you. It takes invariance. So then equivariant cohomology of x is h star of x. And we know from early computations in two-dimensional field theory that this is not the space of states for a two-dimensional gauge theory. So known, this is not the space of states for gauge theory. And what's missing is what are called the twisted sectors, and then it was important to quantum cohomology in that case in the guise of Chern-Ram cohomology. So missing are the twisted sectors. So one space for each group element. And the space that's much closer to what's needed, in fact, it is the space once you put the structure on it. Somehow, because the space comes from maps from the loop space of X mod G, and loops in BG have a monodromy, so you're missing that. So the correct space of states of course is the direct sum over the group elements in the finite case of finite G of the cohomology of the fixed point set with some degree shifts, actually, which I'm not going to get into, everything invariant under G. So before we just had the space where G equals 1 in the equivariant theory. So I think with the benefit of hindsight, what I'm writing here is the twisted sector description of the space of states here. For each group element, we have a space, and we're taking the cohomology over the space G, equivariant for the conjugation action of this system of spaces. So the theorem sort of contains the analog for compact G. Now it's not completely obvious why here I'm talking about fixed point sets there. I didn't take any fixed point sets in X, so something seems to be missing. But to restore it, I have to step down a little bit to explain more abstractly what these things mean. And again, I apologize if people already know everything I'm saying about this, but don't want to jump too fast. So understanding this by going one step down, which is topological quantum mechanics. Quantum mechanics. All you have in that case is a vector space V, and the only partition function you compute that's associated to a point, and your space-time is going to be a circle, the only interesting one, really. And the partition function you compute is a dimension of V, so partition function. Now gauging that means what? Well, gauging that means defining a group action on V. So the define is letting G act on V. quantum mechanics textbook will tell you that the gauge theory, the Hilbert space for the gauge theory will be the invariant subspace for the gauge theory. So the Hilbert space is the partition function for the gauge theory is, so partition function is dimension of Vg. And there's a nice formula for that, 1 of the order of G, summation over G in G of trace V of G. And we can call it a twisted sector formula for the partition function associated with the circle in quantum mechanics. A twisted sector sum formula. Okay. Okay. So now what's happening there is what's fashionably called now a categorification of that. So two-dimensional. So you have to go one category level higher if you want to keep the dimension of manifold the same, but up the dimension of the theory by 1. So to a point before you associate the vector space, the Hilbert space of states. Now here in 2D, to associate a category, a linear category. In our case, we're talking about that as the Fukaya category of X. And to a circle, before you associate a trace or a dimension, trace of the identity or a dimension. And there is a categorical notion of a trace, so in 2D, and that's a Hochschild homology. And in an ideal world, that ought to give you the quantum cohomology of the manifold, and it is true in thanks to monumental work, it's true in some important examples. So ideally, that's meant to be the quantum cohomology of X. But for the purpose of morality, to understand what kind of conclusions you want, you might as well assume it works nicely, and then you see at least what you have to prove. All right, so now we want to gauge that, so clearly we need G to act on the Fukaya category. And we need the Hochschild homology of the invariant in the Fukaya category. And the finite case, we don't need a lot of, we can really work from definition 1. It takes a bit of time and care, but there really isn't anything very deep. There is a twisted sector formula. Which says that the Hochschild homology of the fixed point category is exactly what I've written there. Direct sum over group elements of the Hochschild homology of the action of G. So G has to act by functors in the Fukaya category. You can define their trace. Get a vector space on which G acts. It's a twisted sector formula. An example that's easy to work out easily. So toy example maybe. Instead of a category, just take an algebra or its category of modules. So algebra A. G acts by automorphisms. And Hochschild homology is, well, the zeroth homology is always A modulo the commutators, but there's a formula for the entire homology group. And the, let me not tell you, a fixed point category is a quotient category. So actually, I can tell you the fixed point category. The fixed point category, so A modules fixed point category are modules over the cross product algebra. And then if you like to get your hands dirty to check the twisted sector formula, then you can. Probably I should have put co-invariance here, but somewhere I should have said characteristic 0 over C. So everything characteristic 0. So that's the analog of the dimension of the invariance. Right? So that's what we're looking for. So now it becomes clear what we're missing from the equivariant quantum cohomology. We're missing the twisted sector part, and the only thing to point out is, so maybe let's complete the analogy. So complete the analogy. So now continue the analogy. So before we had representations of G, and one way to understand them, just it's really language, so not a theorem or anything. You can say vector bundles over BG, the classifying stack, is saying nothing now. It gets a little more interesting when G is a Lie group. So G is a Lie group because here we have two kinds of representations, very important. And they're the usual ones. And if you know physics language, we would call them the B-model ones. And have to say nothing about them. We know what a linear representation of a Lie group is. And there are the topological representations, or A-model representation. And these are representation where G acts by its topology. And let me just give an example. X, actually not the same X. Y is a manifold or a space with G action. Then the RAM cohomology, RAM complex of Y is an example of a topological representation of G. So then the RAM complex of Y with differential D is a topological representation of G. And now this point of view becomes a bit more useful, putting something over BG instead of trying to describe it in terms of the action. Because, for example, if G is connected, then the action of the cohomology groups H star of Y is always trivial. But nonetheless, this representation may be non-trivial. G can still act via its higher homotopy groups. And how do you see that? So to see non-trivial action, the non-trivial part of the action, you form the Borel construction. Y sub G over BG, a space over BG. So that is the universal bundle crossover Y with G. And compute its cohomology, if you like, or rather look at the push down of the constant sheaf, the fiberglass cohomology. So this we call it pi, and consider R star of just the constant sheaf C. That's in the derived category of local systems over BG. And this may or may not be non-trivial, so triviality would imply that the cohomology of YG has to be a product. It must be the cohomology of the base times the cohomology of the fiber. But in general, it's just the E2 term of a Spedoré sequence. So non-trivial differentials in the sequence tell you that G actually acts here. That's where the action is hiding. But usually this is just E2 in the ray. So the action is contained in non-trivial differential Berry sequence. And at this point, it becomes helpful to think of it as some space living over Bg as opposed to trying to describe an action of G on something that's kind of invisible to first order and is hiding in some higher order differentials. So the point of view of some things living over the classifying space becomes useful. And of course, this is what we're trying to generalize in the symplectic case. So back in 2D. So now Hamiltonian, we have a Hamiltonian action of G on X. Certainly every group element gives functors on the Fukaya category because it gives a, so G in G has a graph of G star in X cross X minus with the opposite symplectic form, which is a Lagrangian. And assuming the world is nice, it always gives a functor on the Fukaya category. But now what happens is if you have a path between G0 and G1, it gives a Hamiltonian isotopy between these guys. And that gives an isomorphism of functors. So somehow this should suggest to you this more like an A model action, not just the letter and the B model action. So you can identify the action of two group elements if you join them by a path. So somehow you don't see anything moving from a single group element. And the correct statement is that G G acts on the Fukaya category of X via its topology. I could draw a diagram. I don't know how useful it is, but if you want to say, if you move to a world we kill the topology of G, you can actually trivialize the action. So there's a diagram you can draw for that. So G acts on autofunctors of the Fukaya category. If you take the paths in G, the based path from 1 to anything in G, mapping to G, then you get to the inner autofunctors. So these are functors together with an isomorphism with the identity functor. So if you kill the topology, you've essentially trivialized coherently all the functors. And in particular, what you get immediately is that in the fiber of this, you land in the automorphism of the identity functor. And this is, you have to do everything in the derived world. These are the Hochschild cochains. So this is the Fleur cochains, really. These are the units inside the Fleur the quantum cohomology. So the units in Fleur cochains or in quantum cohomology of X. And you could call a top line here the derived Seidel homomorphism. It is I won't explain it, but there are words that do. There's an E2 map from the chains on omega G to the Hochschild cochains of the Fukaya category of X. So if you're lucky. If you're lucky, that's a quantum cohomology of X. But the E2-ness contains information. So I think that's one part that had been. I mean, if I've done anything in the past 5 years and was talking about this, it's actually here. That if you have an E2 homomorphism between commutative algebras that contains more information than saying that you have a homomorphism of commutative algebras. There's structure in there. And that structure was missing somehow from the story. And no way that the structure is missing from a covariant Gromov-Witten theory to get the cage Gromov-Witten theory. So E2 has extra structure. So this one is actually kind of safe even with a very crude, definitely not crude, consistent but fairly easy construction of Fukaya categories. For the next part requires a strictly equivariant version of Fukaya category where, for example, you can make G, everything G equivariant by conjugation. So maybe it's time to just list some bold statements and then hope to work back to my statement there. So I claim we've actually seen that homomorphism before. So from E2 map from, you can go to homology if you take complex coefficients to quantum cohomology of X. Somewhere here, namely. So here I said on the group manifold G, had a local system, forget about equivariance first, had the local system would fiber the quantum cohomology of X. Well, this is a monodromy map. But the whole thing is equivariant under conjugation, so G equivariant. And you can capture that if you want to capture the whole thing. So just the local system, the manifold, you can capture the monodromy map. So capture that by an algebra structure of the equivariant quantum cohomology. So now I've singled out the identity in X where the entire G acts by automorphism. So I can here, it makes sense to talk about the equivariant quantum cohomology at this point. Otherwise, it's just a centralizer which acts. Of algebra structure of this over, well, instead of homology of omega G, you want the equivariant homology of omega G. So maybe I forgot to say that the multiplication on homology is, of course, the convolution on G. So on H star of omega G. G is convolution on omega G, right? That's why it's E2. This one is actually, and turns out, an E3 algebra. In fact, if you take, so here are now facts. So this space has been studied, turns out, lucky for me. So spec of H star G of omega G with complex coefficients. I called that a long time ago BFM of G check because it was studied by Bezrukavnikov, Finkelberg, and Merkovich. And they've shown that, so one, it's a smooth manifold. So if you ignore the grading, the smooth symplectic manifold, complex symplectic manifold, actually algebraic symplectic manifold, with symplectic form of degree 2.
How many concepts
Yes.
does the product come from? Or is it
It's because you've taken the center. These are maps from S2 to BG, so it's sphere topology at Sullivan, so it's E3. Just like it's the maps from S2, free maps from S2 to something. So string product is E3, not E2. Yeah.
But I can't see directly from the point of view.
Well, you've kind of broken the symmetry a bit, but it's an E2 Hochschild cohomology of this algebra, and that's why it's E3. Okay. That's another way to say it. The smoothing with degree, symplectic form of degree 2. So 2, well, when G is a torus, you can see exactly what it is. So it's the cotangent bundle of the dual torus if G is a torus, and in general it is T star T check divided by the Weil group blown up in a specific way. So this is symplectic desingularization of this guy. Symplectic affine desingularization. The only picture I can draw for SL2 maybe some color. So for SL2, so there's a description in terms of a Langlands dual group. That's why I put a G check there, which I don't want to go into. So description, maybe 3 description in terms of G check, and comes from 3D and 4D gauge theory, really, 4D gauge theory. And nowadays has a more fashionable name, much better. I'm not very good at naming things. It's called the Coulomb branch of pure 3D and equals 4 gauge theory. Okay, so for SL2, the dual is PSL2. So we're going to take that, divide by Z mod 2, and blow up just 1 point. So what we're going to get is the following. We're going to get a projection, to the cotangent bundle of the Lie algebra of a torus modulo the Weil group. So that's the original Lie algebra, T mod W, which is just, in this case, C, but sort of a square. There's another projection here to the dual torus mod W, which is also a C. And the space itself contains a fiber T1, T check divided by the Weil group, which is Z mod 2. It contains an exceptional divisor, which is actually spec of the homology of omega G. It's a Lagrangian inside always. And it used to contain a zero section, which it no longer contains, missing a zero section. And the theorem that goes with that is now, well, theorem. I said earlier the covariant quantum cohomology of X is going to be, has to live somewhere here because it's a modulo over the algebra of functions. So maybe let's draw it somewhere here. QH star G of X has Lagrangian support. The projection to this guy is finite. This, by the way, functions here the cohomology of BG, so it's a structural map. And over this Lagrange there lives a bundle or sheaf of categories, so carries a sheaf of categories whose fiber at this point, the intersection of the exceptional divisor, is a Fukaya category of X, and whose intersection with this red line is the fixed point category. So in this case, I didn't draw an intersection. What if I make it come back here and intersect? So here this would be fixed point category. It's a category which generates the gauge theory. And I don't want to give more details, but for the calculus of matrix factorizations, in this space can be used to compute fixed point categories or underlying categories. So recovers fixed point categories, invariant categories, homes between categories, hom G between categories, and so forth. And something else I wanted to say. I'm forgetting. Yes. I won't have time to explain it. Time to close up. In the torus case, I think it's going to be obvious. That's the exercise I had assigned. But so this guy here. This intersection is, the Hochschild homology of this intersection is computed simply by intersecting coherent sheaves, and it is the equivariant cohomology of that local system. So the equivariant cohomology H star G of G Q H star of X is the intersection of the equivariant quantum cohomology with this vertical fiber. Is so QH star G intersect this T1 T check. Oh yes, I didn't say, but no, I kind of said it. Functions on this guy are the equivariant quantum cohomology. So that's the background to the story of how you reduce to that. And now, which part of it is the theorem? Well, if you take away X in the Fukaya category and just say you have a category with some dualizability properties, so it generates a fixed point, so it generates a TQFT, and you have a group acting on it with some properties that I erased, then all of this is true. But if you do that, probably the assumptions you want to write down will not immediately apply to the Fukaya category of anything. And my understanding of the way the subject is working now is, if you want something in full generality, you can't use the Fukaya category as to guide you what you want to prove, and you always have to match calculation of the Fukaya category with calculation of the closed sector via the closed open closed structure map. So somehow one needs, I think, both stories to get to say something about the gauged Gromov-Witten theory. One needs both the story of categories with group actions, and one needs to be able to do the calculation on the space of states in the closed sector and match them together to get a conclusion. So, wow, first time in my life I'm stopping on time.